Hey everyone, welcome back to week 9 of my series where I work through ML through an optimization perspective. So this week I just finished session 3.2 of Boyd, which was about operations that preserve convexity of functions. So this session was actually pretty long and lots of rules, and honestly it's kind of what you expect. If you, for example, if you add two convex functions, then you still get a convex function. So this type of thing. So instead of listing out everything this week, I'd like to do something different, which is just to give you one idea from this section and then give you several examples. So that idea I'll talk about is the pointwise maximum and supremum, and I think there's theory hidden in there that I think is pretty cool. So that's the focus, and let's kind of get on to it. Okay, so first, what's a pointwise maximum? So take any two functions, f1 and f2, that both happen to be convex functions. Pointwise maximum is you simply just take the maximum of each function, and the domain of f is the intersection of domain of f1 and f2. The claim is that this function, if it's the case that f1 and f2 are convex, is also convex. So f is convex if f1 and f2 are convex. So we can easily prove that as follows. So remember, a function is convex if it's the case that the convex optimization of two different inputs of the function is less than or equal to the same convex combination of the outputs of the function. Okay, so we want to show that this expression is less than or equal to this expression. Okay, and we start with just the definition of convexity of f1 and f2 by this inequality here, just by definition. And then we simply do some algebra with a max function, and we've arrived at our expression here, which shows that f must be convex if f1 and f2 are convex as well. So this immediately extends to any arbitrary number of functions, so f1 and f to fm in this case. You just take the max, and as long as all these functions f1, fm is convex, then f is convex as well. And so just visually, this should make intuitive sense. We have a bunch of functions whose second derivative is positive everywhere. So they're curved upwards. And so if you just take the maximum of, these curved upward functions, then just visually it makes sense that whatever you get is also still curved upwards. We can even generalize this even further to what we call an infinite family. So what this means is that we would take some y for some index set a. So this is the index set. Then the function, here f is convex in x. Then the pointwise supremum over the whole family is also convex. Okay, so now let's look at some examples to see how we can show some common functions that must be convex just based on this property here. So first, let's take a look at piecewise linear functions. So if you recall from half planes, each of these elements in the Mach function is a hyperplane. You could think of a hyperplane. And a hyperplane is of course an affine set. So that means it must be convex. And since you're taking the pointwise maximum, the whole thing is convex. And that's it. That's how we show that this f of x is also convex. Okay, our second example is more tricky, but I think this one is really cool. So I think this is actually a good test whether this tool is actually useful or not, because looking at this function, it's not obvious whether it's convex or not just by looking at it. Anyway, so this function, what is it? So first you take, x comes from the set of symmetric matrices. So whatever x is a symmetric matrix. And then what you do is you take the maximum eigenvalue of this symmetric matrix. So this is your function. The function takes an input x, which is a symmetric matrix, and you output the maximum eigenvalue. So how do you reason about convexity here? So first we write the function in its equivalent form, which is the Rayleigh quotient. So what this is saying is that the largest eigenvalue of x is exactly the largest value of the quadratic form y transpose xy can take over all unit vectors y. Now here's the key idea. You fix any particular unit vector y, then the expression y transpose xy is a function of x and is linear in x. You can verify by just writing out the extended form of y transpose xy by the double sum of xij and yj. So this is just the weighted sum of the entries of x. In other words, lambda max of x is a supremum over a family of functions, each which is linear in x. So by the rule we just talked about earlier, this must be its convex. So, that's a generally non-obvious result that falls out immediately once you have this tool. Let's look at our third and final example. The spectral norm, x norm 2, is the largest singular value of x. Or equivalently, the largest amount of x can be stretched by a unit vector. So, it's obviously not, or it's not obviously convex. You don't really know. So the argument is almost identical. You just fix a u and a v, and the expression of u transpose xv is linear in x. Again, it's just the weighted sum of the entries. So the spectral norm is a supremum of linear function of x, and convexity immediately follows. What I found really useful about these two examples is they're not just, toy functions, maybe like the first one, right? Finding the maximum eigenvalue of a symmetric matrix is super common in machine learning. And, the spectral norm shows up everywhere, also in machine learning, and, every other field as well. So to see that they're just, special cases of this property, is really cool to see that, okay, sure, that this is convex. Lastly, I just like to talk about a theorem that I found really cool, which is a characterization of convex functions. What it says is that every convex function, with mild conditions here, can be written as the pointwise supremum of affine functions. So more concretely, it says that, let, f be convex, with the domain of f being the, R of n for some n. Then we can characterize f as the supremum of g of x, where g is affine and g is less than or equal to f anywhere. So f of x equals the supremum over all affine functions that stay below f everywhere. In other words, if you take every possible flat underestimator of f, and f is exactly their ceiling, you can construct any convex function entirely out of affine pieces. So let's think about why this is true for a minute. Well, one direction is obvious. Any affine underestimator g satisfies g of x is less than or equal to f of x, so the supremum can't exceed f of x. So the other direction is the interesting part. At every point x0, you can always find an affine function that touches f exactly at x0 and stays below f everywhere else. In other words, this is exactly the definition of a supporting hyperplane. Or in one dimension, you can think of a tangent plane or tangent line. So at every single point, there's an affine underestimator that's, tight up there. Taking the supremum of all of them, you recover f exactly. So I found this really satisfying. It means that convexity isn't just a shape property, it's an algebraic characterization. A function is convex if and only if it's the ceiling of its own affine underestimators. So you can build any convex function out of flat pieces. So that's the one idea I wanted to share with you guys from 3.2. So the pointwise supremum preserves convexity, and lots of important functions are convex for exactly this reason. Uh, eigenvalues, matrix norms, piecewise linear functions, and there's a bunch of other examples. So the rest of 3.2 has composition rules and perspective functions, which we actually talked about in section 2, which I'll probably get back to next week, actually, um, especially the composition rules. I don't know if you hear from my voice, but I've actually been pretty sick recently. So yeah, it's been hard for me to study after my day-to-day obligations with my job and other things I got going on. But now I'm at week 9, still going strong. So I think I can allow myself to be just a little bit happy of the progress so far. So that said, starting next Friday, I won't have any Wi-Fi for about a week. So hopefully I can crank out a video before next Friday. So anyways, I'll see you guys next week.